This is lesson 7.1, and we're going to be talking about how to graph exponential functions and also about how to solve problems that deal with exponential growth and decay. Now, an exponential function is a function with the general form of y equals ab to the x. An exponential function has an x for an exponent. And also your a value can't be 0. Your b value has to be greater than 0. And your b cannot equal 1 because 1 to any power is just 1. So let's look at a few of these. This first one is y equals 2 to the x. So notice the x is the exponential, or the x is the exponent, so it's an exponential function. So if we substitute in 3 for the x, 2 to the third, that is 8. If we substitute in a 2, 2 squared is 4. If we substitute in a 1 for the x, we have 2. If we substitute in a 0, anything to the 0 power is 1. If we substitute in a negative 1 for your x, so you have 2 to the negative 1, that's the same as 1 over 2 to the positive 1. So that would be 0.5, 1/2 or 0.5. And then if we substitute in 2 to the negative 2, that's 1 over 2 to the positive 2. So that's 1 over 4. So that's 0.25, and you can put that in your calculator. And if we substitute in a negative 3, that's 1 over 2 to the positive 3, which is 1/8. And that is 0.125. Now let's graph that and see how it looks. So when we're at 3, go over 3, you're up 8. All right, go over 2, we're up 4. So it's go over 1, we're up 2. At 0, we're at 1. At negative 1, it's a half. At negative 2, it's 0.25. At negative 3, it's 0.125. So it's just continuing to get smaller. Now, let's look at some other values here. Like if we substituted in a 4 for the x, 2 to the 4th power is 16. Excuse me, I said that wrong. Substituting in a 4, 2 to the 4th is 16. So if we go over 4, we're all the way up to 16. So it gets large very fast. What about if you substituted in a negative 10? So you have 2 to the negative 10th. Well, that's 1 over 2 to the 10th, 1 over 1,024. Now, 1 divided by 1,024, that's 0.00098. So very, very tiny. So when we go at negative 10, we're still not hitting 0. It's never going to hit 0 theoretically. It's just going to keep getting smaller, smaller, smaller as we go out this direction. So because it never hits this line where 0 is, this is a horizontal line. So this is the line y equals 0. It's never going to hit that. We say that this line is called an asymptote. It's spelled like this. And this is what the graph looks like. It's just smaller, smaller, just gradually getting larger, very slowly, and then all of a sudden it explodes. So this is an exponential graph. All right, let's look at another one. Now here, notice this value is 2. This value is greater than 1. Here we have a value that's less than 1, but it's positive though, but it's less than 1. So let's see how that's different. So we have 1/2, and we're going to substitute in 3 for the x. So that would be 1/8, which is 0.125. If we substitute in a 2, we would have 1/2 squared. That's 1/4, which is 0.25. 1/2 to the 1 power is 1/2, 0.5. 1/2 to the 0 power, that's 1. 1/2 to the negative 1, that flips it basically. So you have 2 to the positive 1, and then 1/2 to the negative 2, that flips it. We get the reciprocal, so we get 2 to the positive 2, so 2 squared is 4. 1/2 to the negative 3 is 2 to the positive 3, which is 8. So let's look at that. So we have 3 and then up 0.125, over 2, up 0.25, over 1, up 0.5. At 0, the output's 1. At -1, it's 2. At -2, it's 4. At -3, it's 5, 6, 7, 8. And if we plugged in a -4, it would be 16. So this one, it's going to approach 0, but it's never going to hit it. So again, the line y equals 0 is an asymptote. And so when this is a fraction right here, between 0 and 1, we'll notice that it's going to take this shape. It's called decay. When this value is greater than 1, this is called growth. All right, let's go to the next page here. So we have a little bit more going on. So we have a base to the exponent of x times the number. Now, according to PEMDAS, first you do the exponent. So we do 4 to the power, and then we'd multiply that by 2. So if we substitute in a 3, we would have 2 times 4 to the third. So we can just put that in our calculator. And we get 128. 4 to the third is 64, times 2 is 128. So 2 times 4 squared, 16 times 2 is 32. 2 times 4 to the 1 is 8. 2 times 4 to the 0, so this is 1 times 2, you get 2. 2 times 4 to the -1. And use your calculator when you do these problems. Feel free to do that, because you can easily just arrow back up and change your numbers, your inputs. And this is 1/2. And if we substitute in a -2, so I'm going to arrow back up on the calculator and change that to a -2, I will get 0.125, and arrow up, change my input to a -3, I get 0.031. Now let's graph that. So we're going to go over 3 up 128, which is way, way off the graph. So I'll just put a number up high, value up high. Go over 2 to 32. Okay, go over 1 to 8. Go over 0 up 2. Back 1, we're at a half. -2, 0.125. -3, we just get smaller, smaller. And so it's going to be like this. All right, let's do another one. Now notice we have -2 times 4 to the x. So again, we can plug this in our calculator. And then we just have to go in and arrow up and change it to make this process fast. So we get -128. Arrow back and change it to a 2, the input. -32. Arrow up and change it to 1. We get -8. -2. Put in a -1. We have -1/2. And hopefully you're noticing that these values are all the same. It's just that we're multiplying by a -2 instead. So all of your values are going to be just negative. Your outputs are. All right, and let's graph that. So if we go over 3, we're down 128. So just evaluate really low here. Over 2, down 32. Over 1, down 8. At 0, we're at -2. That's our y-intercept. -1, we're at a half. -2 gets smaller. -3.3. And this is going to look like this. All right, so let's talk about your domain and your range on both of these. So both of these, remember we said in the earlier video that when we're doing cube roots, your domain is all reals because we can substitute in positive values, negative values, and 0. And then because of that, the range will be, actually, it's not all reals here. When we have some extra numbers going on, we see what's happening here. If we look at your range, your outputs, those are your y values. You don't have any y values below 0. And so all of your y values are above 0. So it doesn't even include 0 because the outputs are never going to hit 0. So your range would be y is greater than 0. Your domain here, again, we put in positive numbers, 0, negative numbers, so the domain is all reals. And in this one, if we look at our y values, there are no positive outputs. They're all below 0. So we would say y is less than 0. All right, so general form y equals ab to the x. When b, this value, is between 0 and 1, so like when we plugged in, when we had 1/2 to the x power, it's called exponential decay. When this value b is greater than 1, so when we did 2 to some power, it's called exponential growth. Next, we're going to talk about modeling exponential growth or decay with real-life type problems. So first of all, your general form is a to the t, or a of t is how we would say that, or you could put a y there, is equal to a times 1 plus r to the t. Your a value is the initial amount, your starting amount. Your r value is the rate. Now, when the rate of growth is a positive, this is exponential growth. If this rate is a negative, so if something is decreasing by a certain percent, it's exponential decay. T is the amount of time periods. Typically, it's in years. And one thing to note, it's the number of time periods completed. So if you're doing like an exponential decay problem, or let's say it's a growth problem, and it's been how much money will you have that it's getting 20% per year after 5 years, your T would be 5. But if the problem said at the beginning of the 7th year, how much money would you have? Well, you have to take the number of years completed, so you would use 6, because at the beginning of the 7th year, 6 years would be completed. All right, so here's an example. You invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? So every year you're getting 5% interest. So we have y equals a, and then 1 plus r to the t power. So a is your initial amount right here. That's your a. The account pays 5% annual interest, so that would be 0.05. That's your interest rate. And the amount of time after 6 years, so 6 years are completed, t is equal to 6. So now we substitute those values in. A is 1,000, and then you have 1 plus 0.05, and then to the 6th. And you can substitute that into your calculator, or plug that into your calculator. So you have 1. And it's really important to make sure that you're plugging these numbers in correctly and getting the right answer. So double check that, because sometimes people don't enter it correctly with their parentheses or whatever, and then they end up getting the wrong answer. So your answer should be $1,340.10. So at the end of 6 years, you would have made $340.10 in profit, basically. Here's another problem. Suppose you invest $500 in a savings account that pays 3.5% annual interest. How much will be in the account after 5 years? So this is the initial amount. Your rate, remember we moved the decimal over 2 places to the left, so it's 0.035. That's your interest rate, and the time period is 5 years. So A, your initial amount is 500, 1 plus the rate, and the T is 5. So substitute that into your calculator. And we get $593.84. So go ahead and type that into your calculator. Make sure you're getting that correct. Here's another problem. You suppose you invest $1,000 in a savings account that pays 5% annual interest. If you make no additional deposits or withdrawals, how many years will it take for the account to grow to at least $1,500? So let's see, you put in $1,000, and let me see, what is the rate? 0.05. How long will it take? We don't know, so that's just T. And when we evaluate this, we want to know when this will be at least $1,500, so greater than or equal to $1,500. All All right, now we haven't talked about how to solve an equation when the exponent is a variable. We're going to be learning that later on. So right now, we're going to kind of have to do guess and check. So let's first get this value by itself. So we'll divide both sides by 1,000. And then right here, 1 plus 0.05 would be 1.05 to the t. And we want to know when that is greater than or equal to, let's see, if we divide that, you get 1.5. So let's just make an XY chart and plug in some numbers. So let's see, if it's 5 years, we'll substitute that in. 1.05 to the fifth is 1.27. So let's try 7. Not quite enough. That is 1.41. So that's getting closer. 8. 1.05 to the eighth, that's 1.48, almost there. How about 9 years? There we go, 1.55. So it's going to be, t has got to be 9, so t would equal 9. When t is 9, it's going to be greater than 1.5. All right, last one. The table shows the world population of the Iberian lynx in 2003 and 2004. So in 2003, it was 150. 2004, it decreased to 120. If this trend continues and the population is decreasing exponentially, how many Iberian lynx will there be in 2014? So we have to do some figuring here. So first of all, we need to decide just calculate what rate it is changing here. Percent change can be found by taking the amount of change, so figuring out how much it changed from the beginning to the next time period, and then divide that by your original. So it went from 150 to 120. So the change was down 30. The original was 150. So if you divide that, 30 divided by 150, you get 0.2. It's a negative 0.2, which is down 20%. So in that time period, in 1 year, it went down 20%. So the formula then, we will use that. So A is the original amount. So in 2003, there were 150. And then we went down 20%, so down 0.20. And the amount of time is from 2003 to 2014. So if you subtract that, you get 11 years. And now let's calculate that. And you get about 12.9. So right around 13 then would be all that would be left. All right, and then lastly here, let's take a look at this question. It's a good question. It says, identify each function as linear, quadratic, or exponential. Here, you have an exponent, but it's not or you have a variable, but it's not the exponent. This means 3 times x plus 1 times x plus 1. And if you FOIL that back together, you would end up with a quadratic. So this is quadratic. Here, your exponent is 1. So this is linear. In both of these, you have an x for an exponent. So these are both exponential functions. That's the end of this lesson. Here's the homework that goes with it, and I did work a few of the problems here so you can see how to do those. Let me know if you have questions. Thanks for watching.